Namaste and a very good morning to all of you. I welcome you to my channel, The Outlier. My name is Mithun. In today's video, I'll be talking about a very interesting statistical technique which is called as MANOVA. Even before I proceed to demonstrate how to perform MANOVA using SPSS, may I request you to subscribe to my channel, also like and share my videos. Let me begin by asking a simple question as to what is MANOVA. Where do we use MANOVA and how do we exactly interpret the output or the results from MANOVA? MANOVA is just an acronym for Multivariate Analysis of Variance. I repeat, MANOVA is an acronym for Multivariate Analysis of Variance. In statistics, Multivariate Analysis of Variance is a procedure for comparing multivariate sample means. As a multivariate procedure, it is used when there are two or more dependent variables. So this is a very important point. This procedure allows you to model two or more dependent variables on either a categorical variable or on a scale variable. This procedure is often followed by significance tests involving individual dependent variables separately. Now, even before I proceed to demonstrate how to perform MANOVA in SPSS, let me give you a quick bit of a background about the case study that I'll be working on in today's demonstration. This is a case study which is part of the SPSS case studies. I'm going to use a data set which is called as the PATLOS data set, which comes when you install SPSS into your local machine. In the IBM samples folder, there is a file which is called as patlos_los or length of stay. I'm going to use this particular file to demonstrate MANOVA. I'd like to give you a quick background about this particular case study. As you can see here, as part of the initial treatment for myocardial infarction. When we say myocardial infarction, it is nothing but, in common man's language, you can call it as heart attack. So to treat heart attack or myocardial infarction, a thrombolytic or a clot busting drug is sometimes administered to help clear the patient's arteries before surgery. So this is the context. We are going to use hospital data. We have information about different patients. And as part of the efforts to treat heart attack, a drug which is popularly called as a thrombolytic or a clot busting drug is administered. There are three types of drugs which are given to clear the patient's arteries before surgery. The first drug is what is called as alteplase, which is a relatively newer drug. The second is retiplase, which is again a newer drug. The last is streptokinase, which is an older drug. So we are going to compare the performance of these two new drugs, namely alteplase and retiplase, as compared to the older drug, namely streptokinase. Please also note that alteplase and retiplase are newer and more expensive drugs, while streptokinase is relatively cheaper. So what is the problem statement here? The problem statement here would be to determine whether these newer drugs are cost effective enough to be adopted in place of the older drug, namely streptokinase. Let's make a couple of observations about this particular case study. One of the important observations is, one of the important benefits rather of thrombolytic drugs is that surgery generally proceeds very smoothly, resulting in a shorter recovery period. So the purpose of giving these drugs is that the surgery that you perform will go on smoothly. If the newer drugs are effective, then patients given those drugs should have shorter length of stay in the hospital. Hopefully, the shorter length of stay will help to make up for the greater initial cost of the newer drugs. With this background, let me now proceed to demonstrate how to perform MANOVA using SPSS. As you can see here, this is the initial screen or the welcome screen that I get when I open up SPSS. To load a file into SPSS, I will click on the File menu. Here, let me go on to Recently Used Data. SPSS displays the 10 recently used files. Right at the top, you can see patient underscore loss, patient underscore length of stay in the hospital. I'm going to click on this particular data set. As you can see here, the moment I click on this particular data set, SPSS loads 4 variables in my data set. As you can see, clot solve is one of the variables. This is the clot dissolving drug that we are talking about. The second variable is the procedure of treatment. There are two types of procedure of treatment. One is what is called as PTCA. The second one is CABG. What I intend to do in this analysis is to use clot solving drug and procedure of treatment as the independent variables. I repeat, the surgical treatment variable, namely PROC, and the drug, namely clot dissolving drug variable, will be used as the independent variable. What are the dependent variables that I have? There are two dependent variables that I have. The first one is length of stay in the hospital. The second dependent variable that I have is treatment cost. So these are the two dependent variables. If I had just one dependent variable, I could have used ANOVA, or I could have modeled the relationship between dependent and independent variables using regression. But this is the most important point. Here in this exercise, I've got two dependent variables. Which are these two dependent variables? The first dependent variable is LOS, or length of stay in the hospital, and the second dependent variable is the treatment cost. Let me now go to the variable view to show you the different factors that are present in the independent variables. This is the variable view. Let's look at clot solve. This is the variable. Let us now look at the values column. I'm going to click on the cell for values. You can see here, these are the three different, in fact, 5 different values that you have for drug. -1 represents death on arrival, 0 represents none, 1 represents streptokinase, 2 represents retiplase, and 3 represents altiplase. So level 1, level 2, and level 3, streptokinase, retiplase, and altiplase, we will be comparing the performance across these 3 groups. The next important variable that I have would be surgical treatment. You can see here, this is the label. It says surgical treatment. Let me explore the values for surgical treatment. As you can see here, there are 5 different values. One is -2, which represents died before surgery. -1 represents death on arrival. 0 represents none. Then you have 1, which stands for PTCA. What is this PTCA? PTCA stands for percutaneous transluminal coronary angioplasty. I repeat, PTCA stands for percutaneous transluminal coronary angioplasty. This is a procedure that opens the blocked coronary arteries to improve the blood flow to the heart muscle. You have the second type of treatment, which is called as CABG treatment. CABG stands for coronary artery bypass graft. I repeat, CABG stands for coronary artery bypass graft. This is a surgical procedure which is used to treat coronary heart disease. It diverts the blood around the narrowed or clogged parts of the major arteries to improve the blood flow and oxygen supply to the heart. I'm going to use these two variables, the first two variables, as the independent variable, and the third and the fourth, namely length of stay and treatment cost, as the dependent variable. Let me now move to data view. To conduct multivariate analysis of variance, the first thing that I need to do is click on the Analyze menu. Here, you can move on to General Linear Models. So this is very important. You can choose the option General Linear Models. The second option from the top is Multivariate. You need to click on the option Multivariate to perform a MANOVA. Let me go ahead and select Multivariate. This will open up a new dialog box, which is called as Multivariate dialog box. As you can see here, there are many different boxes. The box to the left side shows all the variables that are present in the data set. Then you have 4 boxes in the right side. The first box represents dependent variable. The second box represents fixed factor. Here you can feed any categorical variable. Then you have another box for covariate where you can supply an independent variable. If you're using any weight variable, you can specify WLS weight. The first thing that I will be doing in this analysis is to specify the dependent variable. Remember, I have got 2 dependent variables. The first is length of stay in the hospital, and the second one is treatment cost. I have specified only 2 variables here. You don't have to limit yourself to only 2 variables. You can specify multiple variables in the analysis. When it comes to clot dissolving drug and surgical treatment, these are the 2 independent variables that I'll be specifying. Both these variables are categorical variables, and hence I'll be pushing this in the fixed factor list. Please observe that I do not have any scale variable which I will be testing for, and therefore I'm going to leave the covariate box empty. The same way, WLS weights are also left as empty. I'm not specifying any variable in these 2 boxes. In the right hand side, you can see there are different options that you can specify. You have a button for model, wherein you can specify the individual effect, the main effect. You can also specify the 2-way interaction or the 3-way interaction effect. Then you have the contrast button, which will allow you to compare between the first level and the second level, or the first and the third level. You can conduct plots. There are very, very interesting graphs and visualizations that are available in MANOVA. In the fourth button to the right-hand side, you can use the post hoc tests. Post hoc tests imply pairwise comparisons of the data. Then you have expectation maximization means, followed by the save button, which allows you to save or create 2 new variables in the data set. Then you have the options button and bootstrap button as well. The bootstrap button is a relatively newer option that is present. If you're using the older version of SPSS, you will not have the bootstrap option. Now, I'll not be specifying each and every option. From the top, the second option is contrasts. I will be comparing the first level with the second and the third. That is, streptokinase has to be compared with altiplase and retiplase. So let me use the contrast button. I've clicked on the contrast button. You can see here, there's a box which says factor. What do we mean by factor? It is showing you the 2 variables that you had specified as the factor. Change contrast. The default option here is none. I can click on the drop-down menu. Once you click on the drop-down menu, there are different types of contrast that you can perform. The first is what is called as deviation contrast, simple contrast, difference contrast, Helmert contrast, repeated contrast, and then polynomial contrast. For the purpose of this video, I'm going to stick to a simple contrast. Here again, you can choose the reference category. Either you can choose the last category as the reference category, or you can choose the first category as the reference category. You have to select first and then click on change. Please observe, as of now, it is saying none. The moment I choose change, SPSS displays simple contrast, which is using the first category as the reference category. Now, let me go ahead and click on continue. Once you click on the continue button, what is the next thing that you need to do? You have what is called as the options button. Let me choose the options button. This will open up a new dialog box. In this dialog box, there are different options. For the purpose of clarity and simplicity, I'm going to choose only some of the important features. One is estimates of effect size. The second one is SSCP matrices, which means sum of squares and cross product. Then you have the homogeneity tests. This is the third option which I'll be selecting. Further, you can choose residual plot, lack of fit, general estimable function, so on and so forth. But for the purpose of this video, I'm not going to choose the other options. I'm going to say continue and then click on the OK button. Now, once you click on the OK button, SPSS is ready with the output. As you can see here, the output is shown in a window which is called as the output window. The first table gives you a high-level perspective about the factors. You have a variable which is called as clot dissolving drug. Please observe that the first category, namely streptokinase, is used as the reference category. The sample size for streptokinase is 250. Streptokinase indicates the older drug, but slightly cheaper. We will be comparing the performance of retiplase and altiplase, which are relatively newer drugs, with that of streptokinase. What is the sample size of retiplase? It is 1412. The sample size of altiplase is 1367. Level 2 represents retiplase. Level 3 represents altiplase. Please remember this, because when we move on to the contrast table, this becomes important. Next, we have the surgical treatment. 1 is the coding for PTCA and 2 represents the coding for CAPG. With this, what I'm going to do now is move on to the contrast results. This is the contrast results. You can see here, there's a lot of information that is being printed. Let me highlight what is going on here. You can see here, SPSS says level 2 versus level 1. I repeat, level 2 versus level 1. Let me go back to showing you the description of level 2 and level 1. You can clearly see when we say level 2, it is retiplase. When we say level 1, it is streptokinase. So effectively, we are comparing the performance between retiplase and streptokinase. I'll go back to contrast results. Very interestingly, you can see the estimate. The estimate is minus 0.279. This is very, very important. It is minus 0.279. Similarly, when you look at the contrast estimate for treatment cost, it is a positive number, 0.441. I'd like to draw your attention to the significance value, which is 0.000. And when it comes to treatment cost, it is the significance level is 0.06. Because we have a negative sign here, I can say that on an average, people who are given Retiplease spend shorter duration of time in the hospital, but they have to spend more money because the treatment cost is positive and it is 0.441. I like to repeat this. There is a negative value when it comes to the contrast estimate. This simply means that people who have received Retiplease will spend 0.27 days, fewer days in the hospital as compared to people who have been given streptokinase. Similarly, when you look at treatment cost, it is 0.441, which means that people who have been given Retiplease will have to spend more money. Question is, are these differences significant? When you look at the p-value, the p-value is 0.000, which is less than 0.05, and therefore you can go ahead and conclude that there is a significant difference in the length of stay in hospital between patients who have received two different drugs. So these differences are scientific and they are real. You can't ignore these differences as accidental. Let's look at the p-value for the second dependent variable, namely treatment cost. When you look at the p-value here, it is 0.06, which is clearly greater than 0.05. Since the p-value is greater than 0.05, you fail to reject the null hypothesis and conclude that there is no significant difference in the treatment cost between patients who have received Retiplease and patients who have received Alteplase. My apologies, and patients who have received streptokinase. So that is about level 2 versus level 1. Now, let's look at level 3 versus level 1. What is the third level? When we say level 3, we are looking at Alteplase, and when we say level 1, we are looking at streptokinase. The contrast estimate shows a negative value. Here, the contrast estimate value is minus 0.579. What does this tell me? The contrast estimate shows that on an average, patients given Alteplase spend approximately half a day less in the hospital and incur a bigger cost. Look at the value here for treatment cost is 1.553, indicating that they are incurring a bigger cost. They're incurring a higher cost as compared to those people who have received streptokinase. One important point here is that the p-value is 0.000 for the first dependent variable. The p-value of 0.000 is again less than 0.05 for the second dependent variable. What is the conclusion that we can draw? Since the p-value is less than 0.05, these differences are not due to chance. The main conclusion that we can draw from this exercise is that the contrast result shows that Alteplase and Retiplease seem to reduce the length of stay of the patient. Thus, the model suggests that Alteplase and Retiplease should be used in place of streptokinase. But before we implement these results, let us look at some of the other important tables as well. Let me now proceed to show you the results of the multivariate tests. As you can see here, this is a table which represents the multivariate tests. You can see here the effect. We have the intercept term, the clot solving variable, the procedure of treatment, and last but not the least, we have the clot solving and the variable procedure, which represents the interaction effect between clot busting drug and the procedure of treatment. When you look at the multivariate statistics, you are able to see 4 different statistics. The first is what is called as Pillai's trace. Then you have Wilk's lambda. The third statistic is Hotling's trace, and the fourth one is Roy's largest root. One question that people usually ask me is, should we look at all the four? Not necessary. If you're a layman and you tend to get confused with so many numbers, my simple suggestion is please always go by the Pillai's trace, because Pillai's trace is more robust. It is a better test as compared to the other tests. I say it is robust because it is robust to the violation of many of the assumptions. However, if you want to gain deeper insights about Pillai's trace, let me just give you a high-level perspective of each of these four statistics. This may be of interest to academicians. If you're a user, you can just ignore this particular explanation and look at only the results of Pillai's trace. That should suffice. Firstly, what exactly is the Pillai's trace? The Pillai's trace is a positive valued statistic. Increasing values of the statistic indicate effects that contribute more to the model. So that is about the Pillai's trace. Let's look at Wilk's lambda. Wilk's lambda again is a positive value statistic, implying that the value will always lie between, the value will always be greater than 0. It will never be negative. Wilk's lambda is a positive valued statistic whose range lies between 0 and 1. So this is a very important point, that the Wilk's lambda value will always lie between 0 and 1. It can't be greater than 1. It will also not be less than 0. Here, decreasing value of the statistic indicates effect that contribute more to the model. So this is a very, very important point. I would like to see the Wilk's lambda being closer to 0, and not closer to 1. Because if the Wilk's lambda value is closer to 0, it means that the effect contributes to the model. Then you have two other statistics, namely Hotling's trace. What is Hotling's trace? Hotling's trace is a sum of eigenvalues of the test matrix. It's a positive valued statistic for which increasing values indicate effects that contribute more to the model. Hotling's trace is always larger than Pillai's trace. Remember, when you compare Hotling's trace with Pillai's trace, we are getting Hotling's trace as 18.08. Pillai's trace is merely 0.9. Hotling's trace will always be larger than Pillai's trace, but when the eigenvalues of the test matrix are small, these two statistics will be nearly equal. When the Pillai's trace and the Hotling's trace are nearly equal, what is the conclusion that we can draw? When the Pillai's trace and the Hotling's trace are very close to each other, it indicates that the effect probably does not contribute much to the model. In my case, you can see there is a big difference between the Pillai's trace, which is in decimals, and Hotling's trace, which is 18.08. That's how you look at Hotling's trace. Then you can also focus on the Roy's largest root. What is this Roy's largest root? Roy's largest root is the largest eigenvalue of the test matrix. Thus, it is a positive valued statistic for which increasing values indicate effects that contribute more to the model. Roy's largest root is always less than or equal to the Hotling's trace. This is a very important point. Roy's largest root. What is the relationship between Roy's largest root and Hotling's trace? Roy's largest root will always be less than or equal to the Hotling's trace. When these two statistics are equal, the effect is predominantly associated with just one of the dependent variables. So this is a very interesting aspect. When the Roy's largest root is nearly equal to Hotling's trace, you can see that the effect, I repeat, when these two statistics are equal to each other, it means that the effect is predominantly associated with just one of the dependent variables. There's a strong correlation between the dependent variables, or the effect does not contribute much to the model. If you are a non-statistician, as I already said, you don't have to worry about each of these statistics. Remember the golden rule that there is strong evidence that Pillai's trace is more robust than the other statistics to violations of model assumptions. And therefore, you can only focus on Pillai's trace and ignore the other statistics. Let me draw your attention to the significance value for the intercept term. I'm only focusing on the first row, namely Pillai's trace. The significance value is 0.000 less than 0.05, and therefore the intercept term is significant. What can I say about the clot dissolving drug? Again, the significance value is less than 0.05. 0.000 is less than 0.05, and therefore you can reject your null hypothesis and conclude that the drug is also significant. The variable drug is significant. When you look at the procedure of treatment, Pillai's trace value has a significance value of 0.000 less than 0.05. Therefore, you can reject the null hypothesis and conclude that the main effect of procedure of treatment is also significant. Last but not the least, let's now focus on the interaction effect between clot dissolving drug and the procedure of treatment. Here, the p-value is 0.000. What does this indicate? The interaction effect is also less than 0.05, and therefore the interaction effect is also significant. So what we can understand from the multivariate tests is that the p-value is less than 0.05, not just for the main effect, but also for the interaction effect, indicating that the main effect as well as the interaction effect are statistically significant. We have a very important statistic here, which is called as partial eta squared. I repeat, this is a statistic which is called as partial eta squared. Again, I beg your pardon, if you're a non-statistician and if you do not have a background in statistics, it might be slightly hard for you to comprehend as to what does this do. In a few moments from now, I'll break this down. What exactly do we mean by the partial eta squared? The partial eta squared is the matrix product of the hypothesis SSCP matrix and the inverse of the sum of hypothesis and error SSCP matrices. So what we are trying to say with the partial eta squared is that it's a matrix product. We are taking the product of two matrices of the hypothesis SSCP matrix and the inverse of the sum of the hypothesis and error SSCP matrices. Now that may be for academicians. Question is, how do we interpret this? Now, this is very important. Large values of partial eta squared indicate a greater amount of variation accounted for by the model effect to a maximum of 1. Let me draw your attention to clot solve. The partial eta squared value is 0.09. 0.09 is not closer to 1. On the other hand, it is closer to 0, which means that this effect perhaps does not contribute to the model. Only 9% of the variation in the dependent variable can be explained by clot solving drugs. Please focus on the procedure of treatment. This is a relatively higher number. It is 0.43, indicating that 43% of the variation in the dependent variable is explained by the procedure of treatment. If the partial eta squared value is closer to 1, we take it seriously. If it is typically greater than 0.7 or 0.8, it means that this effect contributes seriously. On the other hand, if the partial eta squared value is closer to 0, it means that the effect does not contribute to the model. Now, one very important point here is that the partial eta squared for the variable proc is quite large, which is to be expected. Why are we getting such a high value for partial eta squared? The surgical procedure a patient must undergo for myocardial infarction treatment is going to have a much greater effect on the length of their hospital stay and final cost than the type of thrombolyte they receive. In this case, it is enough for the multivariate test to show that clot solving is significant, which means that the effect of at least one of the drug is different from the others. Now that we have understood how to interpret the multivariate tests, you can go on to Box's test of equality of covariance matrices. This is a very important test. What does the Box's test of equality of covariance matrices do? You can see here, it tests the null hypothesis that the observed covariance matrices of the dependent variables are equal across the groups. Now, when you look at this particular table, you're getting the Box's M value. It also displays the F statistic, the degrees of freedom. You have DF1 as well as DF2 and the P value. When you look at the P value that we are getting is 0.000, which is clearly less than 0.05. What does this indicate? This simply indicates that the assumptions are not met and hence the model results are suspect. This is a very important point that I'm making. Since the P value is less than 0.05, the statistical assumptions for us to run a MANOVA are not met. Since the assumptions are not met, the results are suspicious. We'll have to take the results obtained from MANOVA with a pinch of salt. Had the P value been greater than 0.05, it is a good sign. It's an indication that the assumptions of MANOVA are met. Here, unfortunately, the P value is less than 0.05. One important point here is that the Box's M is sensitive to large data files, meaning that when there are large number of cases, it can detect even small departures from homogeneity. Moreover, it can be sensitive to departures from the assumptions of normality. As an additional check of the diagnosis of covariance matrices, we have to look at the Levin's test. So let me go on to the Levin's test of equality of error variances. I repeat, we are looking at the Levin's test of equality of error variances. SPSS gives us a small description here at the end of the table. It says, this tests the null hypothesis that the error variance of the dependent variable is equal across the groups. The first dependent variable that we have is length of stay. The Levin's test is split up into 4 parts. One is based on mean. Second one is based on median. Thirdly, you have based on median and with adjusted degrees of freedom. The fourth option is it is based on trimmed mean. You're obtaining the Levin statistic value with the degrees of freedom. The significance value is 0.000 for length of stay. Similarly, the significance value is again less than 0.05 for the treatment cost. What does this mean? A separate test is performed for each dependent variable. You can see here, a separate test is performed for length of stay. We're also performing a separate Levin's test for treatment cost. The P value is less than 0.05. Since the P value is less than 0.05, we will be rejecting the null hypothesis and concluding that the error variance of the dependent variable, must be equal. That particular assumption must be rejected here. So since we are testing the null hypothesis that the error variances of the dependent variable is equal and we have obtained the P value of 0.000, which is less than 0.05, we reject the null hypothesis and conclude that this particular assumption of equality of variances of the dependent variable, that particular assumption is not met. What is the conclusion? Just like the Box's M test, Levin's test can also be sensitive to large data files. So since the assumptions are not met, we would like to take the results with a pinch of salt. A good idea at this stage would be to transform the dependent variable. That is, we can go ahead and transform length of stay as well as treatment cost. We can apply a log transformation and rerun the analysis. Why am I saying we have to transform? Because the basic assumptions are not met. With this, I have come to the end of today's video. In today's video, we have seen MANOVA, or Multivariate Analysis of Variance. We have seen the assumptions behind MANOVA. We have looked at the interpretation of the Levin's test of equality of error variances. We have also seen the boxes M statistic. Further, we have gone on to check the contrast results as well. I request you to subscribe to my channel, also like and share my videos. Thank you very much for watching this particular video. Have a great day ahead.